So thank you everyone for coming. Today I'm happy to announce that we have Andrei Konovalov speaking on semi-topological K-theory of dg-algebras and the lattice conjecture.
Yeah, thank you for introducing me and thank you for having me. Sorry for starting a little bit late. So today I would like to tell a little bit about some results of dg-algebras, dg-categories. And let me start with a little bit introduction, so dg-algebras and dg-categories. So who are they and why do we care? Basically, whenever so let me just remind the definition of dg-algebra just in case. So dg-algebra is just so you have a carrier of complexes over a field, and it comes with a symmetrical monoidal structure. So we can just tensor two complexes, and this is a nice symmetric monoidal structure with inner home. And dg-algebras are basically just the algebras in this category. So it means that a dg-algebra is a complex such that you have a nice multiplication, such that it's associative, has a unit, all these things. Or if you really hate complexes and prefer spectra, you can think of dg-algebras simply as, I don't know, E1 algebras, which are HK linear for the Eilenberg-MacLane spectrum HK. So, and why do we care? For example, because dg-algebras come from a lot of different structures, from a lot of different fields even. So, for example, the example that would be relevant for me is that whenever you have an affine variety, which simply means that it's something given by a finite number of equations in a affine plane. So you have some equations like, I don't know, x1 squared plus x2 equals to 0, or I don't know, x2 minus x3 equals to 0. Then you have the corresponding ring of functions. For example, if this lives in A3, then this ring of functions will be, sorry, let me check. Sorry, for some reason my pencil stopped working for a second. Okay. Oh, okay, it works now. Sorry, do you see what I'm writing? So before that I wrote two equations. Did you see them?
Yes, we do.
Okay, but for some reason they disappeared.
I guess so, yeah.
Okay, I don't know what's going on, but let me just continue. So, for example, if you have two equations, something like this, I don't know, minus x2, 4, this gives you some algebraic variety, and you can attach to it its corresponding ring of functions, which is just basically this ring of polynomials modular the ideal generated by these equations. So whenever you hear the phrase affine variety, just think of a system of equations or about the ring, which basically contains all the necessary information about the variety itself. So the basic point is that to a affine variety, one can attach a nice ring, or actually one can think about this ring as just a dg-algebra corresponding, which sits in the degree 0. In fact, to any variety, for example, to projective variety, which are just some things glued from affine guys, one can also attach some dg-algebra. One can also attach a dg-algebra to, for example, nice group, a topological group. Simply, one can send a group to the corresponding group ring. So this assigns to a group dg-algebra. One can generalize this example and consider any topological space X and assign to it the corresponding space of chains on loop spaces on X valued in K, for example. This is some dg-algebra, so it's a complex, and it's also a dg-algebra where multiplication comes from the concatenation of loops in omega x. And this is the dg-algebra which is really important for rational homotopy theory or for A theory, stuff like this. And one can also put here a lot of other words like symplectic variety and other stuff. But basically, in a lot of situations, one can find some dg-algebra or more generally a dg category. So a dg category for me, dg category is just some mild generalization, in fact, of a dg-algebra. A dg category is just a category enriched over complexes. So basically, for every two objects, you have a complex of morphisms between them. So whenever you have two objects, x and y, home from x to y is a complex and not merely a set. Then we call this category dg category. Well, and you also, of course, need some nice properties about associativity of composition, about existence of units, and so on. Basically, you want a category which is enriched in the symmetric monoidal category of complexes. So whenever you have a dg category, a k-dg category, you can try to study it and assign to it some nice invariants, some k models or complexes of vector spaces or spectra and stuff like this. And actually, in several of these examples, for example, for the case of projective variety or symplectic variety, there is no canonical dg-algebra attached to your thing. In fact, you would prefer to assign to it a dg category. So examples of let me just say some examples of dg categories. So you can consider derived categories of classical rings. You can consider derived categories of schemes, I don't know, stacks, derived stacks, and so on, or categories of perfect complexes in them. So, for example, you have categories like perf A for a classical algebra A, which lives inside all A models. And basically, this category contains a lot of information about your ring, which you start from. And on the other hand, a lot of properties of this category can be recovered already on the level of A for any choice of generator for any choice of A, such that your dg category can be represented as the category of A models. So there are some other examples of situations where dg categories come from, but basis yoga is that you get them from all the different fields, and sometimes you get the same answers from different fields. For example, there is this nice example that I really love, though it's a little bit stupid, but simple. It's like, for example, one can consider the category K, the dg-algebra K plus minus 1, or the corresponding dg category perf of K on X plus minus 1, just the dg-algebra of Laurent polynomials. And this comes already, this scheme appeared already 3 times on this board. For example, one can consider this as algebra corresponding to GM, which is basically the affine variety given by the equation xy equals to 1 inside A2. So this, if you consider the linear functions, it's k of x, y modulo xy minus 1, and it's isomorphic to this guy. It also appeared as a group algebra for a group Z. And it also appears if you consider, for example, the tangent bundle to a circle, and consider it as a symplectic variety, and consider the corresponding Rapp-square category, then this Rapp-square category would be equivalent to this guy as well. So basically, you can get the same categories from different sources, and this could allow one to understand something about algebraic variety and to use this theory in order to understand something about the group, the corresponding group or stuff like this. Anyway, sorry if it was a little bit I don't know, too vague. Let me come to some more concrete stuff. Basically, we would like to study those KG-carriers by assigning to them some complexes of K-vector spaces or spectra, some cohomology series, basically. And in fact, in a lot of these situations, for example, for nice varieties, for nice symbolic varieties, we have already some nice cohomology series, and that's a nice start, nice point where from which we can try to generalize things, and we can try to invent things which are analogous to things in the classical setting. For example, in algebraic geometry, there is, I'll actually restrict to the case of complex numbers from now on. Let me actually switch the color. So from now on, I'll restrict to dg-algebras and dg-categories over complex numbers. And even if you consider a little bit more classical object, like a smooth projective variety of complex numbers, or just actually it can be a little bit generalized, then well, whenever you have a variety of complex numbers, you can look at the corresponding topological space and consider its and there are those differential forms which form you a drum complex, and you can consider smooth drum complex, or in fact holomorphic drum complex or algebraic drum complex. They will all give the same answer. Well, they'll give you equivalent answers, which are called drum cohomology. And the subject of classical Hodge theory is that, in fact, this guy comes with a lot of extra structure, which really helps to understand how it works. In particular, it comes with Hodge decomposition, which basically decomposes this guy as, which basically decomposes, for example, nth drum cohomology of x as a sum of HQ x omega p over p plus q equals 10. Those are just some coherent cohomology of shifts, or if you know something about harmonic forms, those are just given by some vector spaces generated by some nice harmonic forms. And this has also a nice integral structure, meaning that inside those guys are vector spaces over complex numbers, but actually inside this there are canonical rational subspaces, or actually even integral guys. You can just consider X as a topological space. So whenever you have a smooth complex variety, whenever you have a variety of complex numbers, you can just look at the corresponding set of complex points with the standard topology. And then you just have the classical singular cohomology groups. And in fact, again, by de Rham theorem, you know that if you consider integral basic cohomology groups and tensor them with complex numbers, you'll recover smooth drum groups, smooth drum cohomology groups. So in particular, these C vector spaces come with integral, rational, or I don't know, real structure. And for example, this real structure comes in handy in the way that you have actually a complex conjugation. You have a complex conjugation here on this guy, and this complex conjugation, in fact, leaves, like, for example, real basic cohomology groups. It doesn't act on them. It leaves them where they were. So, and in fact, it's like switches PQ and QP pieces around. So question, and for example, like a nice corollary of this is that whenever you have a smooth projective variety over C, in particular, whenever you have, for example, smooth projective variety over C, since, as I said, HPQ and HQP are swapped, you know that the dimensions are the same. So in particular, whenever you have smooth projective variety, its odd cohomology groups are even dimensional. For example, H1 and H3, and all these guys are even dimensional. So okay, so there was a set of conjectures by Maxim Kontsevich and Katsarkov, Pantev, and other guys who suggested to look for analogs of this Hodge theory for nice dg-algebras and dg-categories. In particular, there is a nice. One would like to define differential forms for general dg-algebras, define the RAM complex, and define this filtration, which gives you this spectral sequence and corresponding composition, and so on. And one could think that it's too courageous that one cannot hope for such a thing. But in fact, it turns out that one can define a lot of things for dg-categories. One can define what it means to be smooth or to be proper for a nice dg for every dg-category. One can define what it means, what are differential forms in a sense, and what are drum cohomology groups, and so on. So if you ever heard there was like cyclic cohomology groups, then you probably already heard about this. So there is this classical theorem belonging to Hochschild, Kost, and Rosenberg, that whenever you, for example, start from a nice, whenever you consider a fine variety, Hochschild cohomology groups of perf on your variety are in fact just like nth Hochschild homology groups of your affine varieties are in fact just omega n of x over c. So whenever you have an affine variety, you can recover its the differential forms on this guy simply in terms of the corresponding dg-category. And one can also recover like drum complex and so on. So there are those HKR type statements which basically say that for smooth projective varieties, periodic homology behave like an analog of drum homology groups, and Hodge homology behave like analog of differential forms or corresponding global differential forms, or like the high versions. And there is a theorem of Claydon that in fact there is an analogous spectral sequence from Hochschild to periodic, which generates at the second page, given a picture analogous to classical Hodge theory. Sorry, actually, I should have probably said it in the very beginning, but nobody asks questions, and I should probably stop for a minute. And like feel free to interrupt me at any point and ask questions, or I don't know, ask them in chat. I'll probably see. But actually, I mean, there is a lot of. I decided to spend like 20 minutes on some kind of motivation, but I believe it would be nice to at least remember this nice picture that about like about translating some intuition from geometry to like general dg-categories and stuff like this. So, are there any questions? Okay, then I'll proceed. So let me say something about the problem I actually most interested in. It's the problem of finding an integral structure on periodic structure homology in the integral case. So I remind you that let's recall that whenever one has a smooth projective variety, or actually any variety of complex numbers, one has drum cohomology groups on X, complex valued, and one has, for example, basic cohomology groups on X valued in Z. and this are related by hb of x times over z by c is just equivalent to h-gram of x. So there is a nice integral structure inside h-gram, and it comes in handy for a lot of stuff in Hodge theory. For example, it gives you extra it gives you some extra rigidity whenever you consider like families of varieties and try to understand how Hodge structure varies in families. It gives you like already real structure gives you some kind of complex conjugation, and after you prove some that filtration and this complex conjugation interact in a nice way, you already know this statement about odd dimensional, even dimensionality of odd cohomology groups, for example, and all the stuff like this. And there was this question of conservative partial. So we think of HP as analog of the round cohomology groups. So, and again, we know by Canadian theorem, for example, that it comes with analog of Hodge filtration. So the equation is, can we find an analog of beta cohomology groups here? Which basically would mean that we find something which tensor we see will give you jump cohomology groups back. And in fact, basically, of course, we want all the nice integrality. So we want it to be a functor on the category of dg-algebras. And some possible applications of proving existence of such structure would be, like, for example, the first application is that, as I already said, there is this generation of spectral sequence proved by Canadian, analogous to this, but generation of spectral sequence alone doesn't give you some canonical decomposition. So it just gives you some, that there is some filtration, you know graded pieces, but whenever you have a filtration and you know graded pieces, there is no canonical way to say that your object is equivalent to a direct sum of its graded pieces. But again, I'll not go in detail, but existence of this nice complex conjugation allows one to obtain a canonical decomposition. One can also define some nice categories, nice structures from classical algebraic geometry, like intermediate Jacobians and stuff like this. And a partial answer to this question of conservative quantity was already used to prove some new cases of integral Hodge conjecture by Alex Perry. And also there are a lot of actually those conservative quantity were actually motivated a lot by mirror symmetry, which would allow one to transpose some properties and even, I don't know, some invariant, some computations from algebraic geometry to symbolic geometry and back again, actually using that there are some equivalent categories coming from both of these fields. Okay, so note that whenever, again, as I said, whenever x is, sorry, note that, as I already said, whenever x is, say, a nice variety, HP of x is actually equivalent to jump cohomology groups to periodized. So you just take HP0 is just the sum of all, even jump cohomology groups, and HP1 is just the sum of all odd dimensional, all odd jump cohomology groups, and so on. And rationally, and as we know, this guy in classical situation already has an integral structure given by beta cohomology, but rationally, two-periodization of beta cohomology is the same as just rational topological K-theory. So this motivates the name that we want to look for some invariant which we would like to call topological K-theory, such that it's a functor and it comes with a natural transform to HP, such that
Looks like we've briefly lost our speaker, but not the iPad.
Hello, can you hear me?
Yep.
Sorry again, there was a problem with, probably it was a problem with connection on my side. Okay, by the way, are there any questions at this point? So, okay, so engine one constructs a function, a spectrum valued function, which is a nice invariant. In particular, it respects Morita equivalences of dg-algebras, whatever they are, and it's localizing, which basically means that it's kind of cohomology theory. For example, whenever you have three categories, T1, T2, and a quotient, for example, the real quotient of T2 modulo T1, then you'll have an exact triangle of K-top of the corresponding topological K-theory spectrum. And this invariant comes with a map from algebraic K-theory of dg-algebras and with a map to periodic cyclic homology, such that in fact the combination of these two maps recovers the composition of the trace method, the trace map from algebraic K-theory to cyclic homology, and just this natural map. So and like there is this property that whenever we restrict to the classical case, so we restrict to the case of dg-categories of nice varieties, then topological K-theory of those dg-categories is actually the topological K-theory of the corresponding topological space. So topological K-theory is topological K-theory. That's great. And let me state my result, and then I'll spend last 20 minutes trying to define and I will define this invariant and say a bit about the proof of the following result. So one of my main results is that I'd like to talk today about is that in fact this this map, topological chain character, actually does provide a periodic homology with an integral structure in a number of nice cases of interest. For example, whenever your dg-category is actually perf of A for a connective dg-algebra with a reasonable H0. So it's this map is also an equivalence whenever it is derived category of nice derived algebraic space. Actually, the same this statement remains true if you even put here something like nice derived stacks.
I think we just lost your screen share.
Okay, that's strange. Thank you. Just 1 second. Okay, maybe it's again some problem with. Okay, I think it should be got better now. Just a second. Oh, okay, it seems to work. As I actually let me make a bit a small remark before that. Again, I said some words about dg-algebras, and I said some words about dg-categories. But the thing that I like to also mention that it's the difference between these guys is not that large. So whenever you have an IDG category, and nice is a really mild assumption. Then it's actually equivalent to the category of the form perf A, where A is just some dg-algebra. And in fact, so if you want to restrict to dg categories coming from the nature, I don't know, then in fact all the dg categories have a description of perf A for some dg-algebra, but the catch is that you can find several different dg-algebras and like find some different dg-algebras and get the equivalence like t equals to perf A and t equals to perf B for different dg-algebras A and B, which is this concept of Merita equivalence of dg-algebras. And basically choosing this dg-algebra is kind of similar to choosing a basis in a vector space. So it's nice to do. Sometimes it helps to do calculations, but the very reason I'm talking about dg is that it's kind of more natural setting to study, kind of more coordinate free. But another reason I mentioned this is that in fact those first and second first prime examples are kind of also cover kind of half. Well, actually, it's not speaking true, but they are considering some nice dg-algebras which are connective, meaning that they live in positive homological degrees, and they are not very wild in the degree 0. So whenever you have a thing like this, you know the statement about integral structure on HP, and this is covers again a lot of dg categories coming from, for example, coming from the group algebras. And there is also this example with derived algebraic spaces, and there is also a nice example that you can consider infinite category of local systems of complex of vector spaces. And if you put some condition on pi 0, on pi 1, and also I would like probably to have pi 0 equal to point. Then you can also understand topology 0 of this guy as well. But actually, I'm kind of using Farrell-Jones methods here a lot. So it uses some equivalent homotopy theory to understand topology theory of these guys. Okay, let me finally say something about the definition of topology theory and the way and how one can actually prove such kind of statements. So actually, before even giving the definition, let me just mention some intuition that I find important to keep in your heart sometimes. Whenever you have a nice variety, again, like I don't know, X smooth affine variety, for example, smooth affine variety. Actually, affine is not important at all here. Then, actually, so the simplest kind of K groups that one can assign to it are algebraic K0. So one can assign to it algebraic K0 of X, which is something defined, which can be defined as you just consider all algebraic vector bundles on X and take the modular equation that whenever you have I don't know, 3 bundles, E1, E2, E3, and an exact sequence of them, then you want the class of E2 to be equivalent to the class of E1 plus the class of E3. And I'm not saying what the high algebraic K-theory is, because but basically it's but basically one can assign to X a space or even a nice spectrum K of X, such that its zeroth homotopy group would be equivalent to K0 of X. But we kind of doing the same. We kind of putting those kinds of relations, but we doing this in a homotopically meaningful way. Okay, and one can also assign to X its topological K0, of the corresponding topological space. And it is just, you consider the space of complex points of X with complex topology, you consider topological vector bundles, again, modular equation like this, for example. But there is actually a intermediate, and there is also the whole topological K-theory, which is a two-periodic, for me, it's a two-periodic spectrum, which is a map spectrum from sigma infinity x n plus to ku. But actually there is an intermediate guy here called semi-topological K-theory, which receives the map from here and has a map to here. And this semi-topological group, K0 group, can be defined simply as you consider algebraic K0 of x. And you take it modular algebraic equivalence, where you basically say that two bundles, I don't know, E1 and E2 are equivalent algebraically. Whenever you can find some curve, connected curve, and some bundle E, bundle on x times this curve, such that and this curve comes with 2 points, say, I don't know, x1 and x2. And we say that two bundles E1 and E2 are algebraic equivalent. You can find a curve, 2 points on it, and the bundle on the product, such that E restricted to, such that E restricted to x1 is E1, and E restricted to x2 is E2, which is actually similar to the standard algebraic equivalence relation on cycles in cycle theory. Okay, and in fact, it turns out that one can define the semi-topological K-theory for general dg-algebras, and it's kind of important intermediate step. Let me say the definition. So, the shortest definition I know is that the category of finite type schemes over complex numbers, basically category of fine varieties of complex numbers, comes with this functor to topological spaces, which just assigns to variety is corresponding topological space, and then we can kind of extend this functor to all pressures of spaces on this nice category. So basically, what it means? Basically, it means that basically it means that whenever we have a functor, whenever we have some functor here, a functor f, we can say that this, okay, there is this functor f which we don't understand, but there are a lot of unit guys, there are a lot of representable guys, which are just guys of the form homes to some affine scheme. And for every affine scheme, we know what is the functor of complex points. So now we want to say that now we define the functor of complex points or a topologicalization functor, simply by saying that, okay, we introduce f as a limit of representable guys, and we compute this functor of complex points on each representable guy, and define this area as the limit of these guys. Or this means this is what is called usually Lefkan extension of this functor along this map. And then one can stabilize both categories. So there is this functor sigma infinity plus spectra here. There is sigma infinity plus spectra here. This category is actually the stabilization of this category. So by universal property, basically, this functor can be extended in such a way that it would commute with, it would behave nice with respect to distinguished triangles. Okay, and the motivation for such a deviation, one of the motivations is that if you consider a guy here given by just algebraic K-theory, so it takes an affine scheme and it gives you back algebraic K-theory of this affine scheme, and you compute this realization guy on this functor, then you will recover the connected negation of the topological K-theory spectrum. So this is kind of nice, and for me, it was a little bit unexpected when, the first time when I saw it. But in fact, it kind of boils down to the fact that okay, you have BGL kind of guys here, so basically stacks, classifying stacks for general linear group, and here they map into like B of GLM corresponding space logical points, but in fact it's just homotopy equivalent to BUNs. So in the end, it's not very surprising, but kind of nice, I think. So, and using this, one can define simple K-theory of general dg-algebras via this formula. It always will be a KU model, basically by Manuel properties of functions in this picture. And then one can just define topological series spectrum as a semi-topological series spectrum where you invert the bottom element. So you basically tensor this with Q large over Q small. And it turns out that whenever you are in the geometric situation, so you consider perf X for a smooth variety X, the zeroth homotopy group would be in fact this homotopy group that we discussed earlier. Okay, okay, and how do we? So we gave some definition of this guy, but it has a lot of flashback K-theory guys in it. So basically, it's basically some kind of calamity of flashback K-theory guys. And how can we understand such a thing? Well, flashback K-theory is very difficult to understand and compute, but one of the most important instruments to understand it is trace methods, which basically is study some new invariance properties of different invariants. For example, there is this. So let me give a definition. So I would tell a map of A to B. So whenever we have a map A to B of connective dg-algebras, connective just means that they live in positive non-negative homological degrees. It is called derived null extension. Well, okay, let me actually give another definition. So definition due to lambda, this map is called truncating. It is called sorry. Okay, sorry again. So let me say that this is a derived null extension. If H0 A to H0 B is just a surjection with an important kernel. And there is this classical theorem of Duns-Goodwin-McCarthy, which basically says that the fiber of this trace map that we already mentioned, fiber of this trace map from H K-theory to HT minus, or actually one can put TC here to be fancier, that the fiber of this map preserves how to say it. Let me say that it is null invariant. And when I say null invariant, I mean that whenever you have A to B a null extension, the value of your invariant on this map is an equivalence. Okay, and this is a really powerful theorem that allows for a lot of which helps to compute algebraic K-theory and was used a lot during the last 30 years, I guess. This theorem was kind of motivated and in fact was used in the proof of the following theorem, that semi-topological K-theory is in fact also derived invariant. So for every map of connected algebras, semi-topological K-theory computed on this map is an equivalence. So okay, I have only 3 minutes left. So let me let me not go into a proof. Let me just say that it uses exact trace methods, and it also uses computer understanding of how realization behaves on guys like HH or HC minus or HP. And basically that's it. But let me also mention that by the theorem of Lantama, being derived invariant also implies that your fund restricted to classical schemes satisfy CGH descent, which basically means that whenever you have a singular scheme, you can use it, and you can find some nice resolution singularities. You can compute your invariant on a single scheme by knowing it for like all the smooth schemes. Basically, you need to know it for the resolution of singularities and for resolutions of singularities of the exceptional divisor and the singular logs. Okay, and let me also mention that, as I mentioned, the one of the most powerful, one of the fields where classical Hodge theory is most powerful is when you consider variations of varieties. So you have some number of equations, and you just have some set of parameters, and you like just reform your equations using these parameters. And there is a lot of nice theorems that Hodge structures behave nice when you consider nice deformations. And let me finish with saying that you can define that you can consider deformations of dg-algebras over nice basis, and define actually most of the stuff there, and it will be actually really nice to understand the behavior of topological K-theory with respect to those deformations. In particular, again, I kind of expect that for nice deformations, topological K-theory will not vary at all, like it is in the classical situation. If you have a nice family of varieties, then they are topological equivalent. In particular, singular homology and topological K-theory on them are the same on different fibers. So that's one thing that I'm interested to look at. Okay, I guess that's it. I would be happy to hear more questions.
Let's all thank our speaker. And are there any questions for Andrei? So I have 2 questions. The first one is your current work really working with the relative version and working out what conditions and what happens there with the deformations?
So the question is kind of, what do I mean by deformations? So I mean, sorry, can you just phrase the question again?
Oh, just is the relative version something you're currently working on writing like a theorem statement for?
Well, I wouldn't. Actually, I don't have strong theorems now. It's mostly about some computations in. It's mostly about some constructions, and now I'm trying to understand if the relative chain character is correct one. Is the correct one if it gives the correct answer in case of interest and stuff like this.
Are there any other questions? I guess my other question was, so you've been working with this topological K-theory, and we're able to show in a lot of cases you get an equivalence that you want. Is there any other potential theory that would maybe work in some other cases?
So actually, the conjecture is that topology that you don't need any other theory. I mean, of course, we want to have one, but we don't want to have, I don't know, a neutral structure for each particular dg-algebra, because I mean, we already have it kind of. If you have a complex vector space, you can just choose a basis. But we basically want to have a uniform environment for all dg-algebras, and we want the natural transform of we want to have a natural transform of functions from F to HP with nice property. So conjecturally, topological K-theory is an equivalence for all smooth and proper, or actually really general class of dg-algebras. So I don't know any nice counterexample. I know only really crazy counterexamples for which you don't actually expect anything like this to be true. So, but the thing is that, I mean, the methods that I used behave best with the connective dg-algebras, basically because I'm using trace methods, or some stuff which can be easily glued from connecting guys, or I don't know, glued from connective guys, or some other guys that people understand. And in general, well, again, as K-theory of general dg-algebras, or I don't know, general ring spectra, which are not necessarily connective, is really mysterious, and you don't have trace methods and stuff like this. Topological K-theory should be simpler, in fact, than algebraic K-theory, but you cannot understand it via those kinds of methods, at least. So the answer is conjecturally yes. We expect that the topological theory would provide the lattice in general case, but we simply don't know.
Okay, thanks. Any other questions? Well, if not, let's thank our speaker again.